Yeah, so just as an intro to everyone who's joined, this is like the last part of the mini series on stellar astrophysics. This will be a talk on Astroseismology by Anhads of BSMS 2019. So yeah, whenever you're ready, you can start them.
Yeah, so I'll start. Uh, yeah, so is my presentation visible? Like, is it in the presentation mode?
Yeah, I'm not in presentation mode for me.
It is not.
No.
Okay, let me then present again. Is it fine now?
Yeah, it's fine now. Yeah, it's good.
Okay, so I'll start with this. So basically, this is the third part of the stellar astrophysics talk series. So in the previous sessions, you might have, if you have attended, then you must have known that we discussed about stellar structure equations, and in the second part we discussed about stellar evolution. I will be recapping some few parts of it which are relevant to this talk series, this final talk. So I'll I'll start with the astroseismology talks now. So basically, I've divided this into four parts. The first part is the introduction. Then we will go with what is astroseismology. Then what are the applications, like what do we get from it? What are the benefits that we get from doing astroseismology? Then we'll go with the concluding remarks, which includes like what results we have obtained from the astroseismology and some future missions which can help in the future research in astroseismology field. So yeah. So I just wanted to give a small disclaimer that I won't be going through much mathematical equations in this talk. I will basically just give a broad overview of the astroseismology field because it is so vast. I couldn't like give go into details for this small talk. So I'll just go with a broad overview. So, yeah, I'll first start with a quote from Sir Arthur Eddington, which is a famous astronomer in this who has worked in the field of stellar structure and stellar evolution field, stellar astrophysics basically. Yeah, so he goes on saying that our telescopes may probe further and further into the depths of science, but how can we ever obtain certain knowledge of that which is being hidden hidden behind substantial barriers? What appliance can pierce through the outer layers of a star and test the conditions within? So yeah, we all know that since like we are building bigger and bigger telescopes and better telescope, and now we are able to get better resolutions to farther and farther of space. But how do we actually go inside a star and measure the properties inside it? Because we cannot send any probes which can withstand the high temperature and pressure which a star has. So apparently we cannot probe probe the interiors of a star directly. So instead of probing it directly, we use as like how we probe inside our Earth. So we basically do seismology there. So as well, I'll go on talking about exoseismology in the next session. So uh, next page. Yeah. So I'll do first recap some from the previous sessions. So in the first session, you must have seen these equations. These are basically the stellar structure equations. So these equations show, the first equation shows that there is mass. We are assuming mass conservation in a star. There's also hydrostatic equilibrium, energy. Notice that this hydrostatic equilibrium and energy conservation are mainly hydrostatic equilibrium is mainly for a static star. This both of these conditions. So this will be changing throughout the lifetime of a star, but uh, for our time scales, like the region in the time region in which we are considering our pulsations, these are negligible. So we'll discuss more on the time scales in the next slide. So yeah, this is basically we have our mass equation, then pressure equation, then luminosity and temperature, which can be divided into two parts depending on radiation and convection. And these are other equations which helps us link all these unknown parameters between these equations. So basically, what from these equations we can basically construct a static star. So uh, so what's the problem in constructing a real model of a star? Like so far, why haven't been we have been able to? The main problem is that since these parameters, we need these parameters at every point inside the stars, and we cannot. And in the last slide, we saw that we don't have any physical probe which can go inside and find measure these parameters. So instead of going inside, we use seismology to basically get these parameters deep inside the stars. And using this astroseismology, we can basically connect these equations and test our theory that these equations, we can test these equations whether these work, and like whether these will able to build a proper build a good stellar model or not. Okay. Yep. So like in the previous slide, I talked about time scales. So basically, you can talk about time scale as it can be. We just needed it in the order of something and not a specific value. So a characteristic time scale can be expressed as a physical quantity divided by the rate of change of that physical quantity. So so let us consider the time scale of this pulsation. So the pulsations that we have on the surface of stars. So we can consider the length to be near about the radius, and the velocities to be uh, this. There should be an under here. Sorry for that. There should be an under root here, under root gm by r. So this is basically the length scale of a star, and this can be a velocity, which is the surface velocity. You can take it as the orbital velocity on the surface. So this is the dynamical timescale of pulsations of the variations on the surface of the star. So we can get this approximation to be like under root 1 by under root g times rho. And for our own sun, this can be calculated. This dynamical value will be around tens of minutes, something like that. So yeah, so in the previous slide, I talked about like why can we ignore these conditions? Why we can take energy conservation and hydrostatic equilibrium is that because these energy conservation, the lifetime of nuclear reactions and the lifetime with the time scale it involves for contraction, these are basically on the scale of millions or billions of years. So, and these are in the time scale of minutes. So we don't have to worry about those effects like nuclear energy causing some vast deviations or like stellar evolution. It is becoming a red giant or something like that. We don't have to worry about that. Okay, so moving on to the next slide. So we now look at why do these stars now pulsate? Like what causes these pulsations? So yeah, from these pulsations can occur due to changes in the stellar structure. Now, what can cause these changes, this small perturbation in the stellar structure? So these can be a result of nuclear energy release, which can cause mild. These basically, if you can like consider some amount of energy releasing from the core. So it can be released from a local region, which can cause perturbation in the whole star and disturb its hydrostatic and thermal equilibrium, basically. So at like consider, let me draw something. Yeah, so consider a star, and this is the core. Sorry for this weird circles. Yeah, so consider a small amount of energy coming only from this side. So basically, if this region is heated up, this will basically like if this star is basically a fluid or a big amount of gas. So basically, this small portion can get heated up and expand. So these expansion and contractions can occur in the star, and these can cause these changes in the stellar structure. So basically, these can perturb the hydrostatic equilibrium or thermal equilibrium of the star, and it can result in those pulsations. Uh, yeah, basically. Yeah. So, and what other stuff can be there? There can be rotation of stars. There can be change in those magnetic fields on the surface, which can again result in disturbance in the surface of the star, and again cause pulsations. There can also be external perturbations like nearby supernovae occurring, whatever, and many small perturbation can or may lead to any kind of pulsation. So, what kind of variations or pulsations do we see? So, we can see changes like changes in the outer structure of the star. We can see changes in the luminosity, and we can also see changes like pulsars. Like if you have heard about pulsars, so pulsars is basically a type of star which emits X-rays in this axis from their magnetic poles, and it may rotate like this on this axis. So we can get such type of pulsations as well. But in this talk, we will mainly focus on pulsations which are caused due to the structure and luminosity, or mainly from the structure. Okay, moving on to the next slide. Yeah, so what we'll be looking at? We'll be looking at changes on the star's surface mainly, and how do we measure them? So basically, you have seen that we will be measuring this changes on the surface of a star. So how do you think would we be able to measure that? So basically, uh, when the star's surface change, either it will contract or expand at some point. Like if you are looking from a direct, like if you are observing from this side, you can either observe this part to be contracting or expanding. So basically, you can basically find a Doppler shift in all the spectral lines at each part of the star, like whatever is visible to you, and you can make a spectrogram, or like you can make a graph of it, and check like what is the radial velocity of all those of the star surface which is visible to you. And we can also measure the changes in luminosity, which is basically the intensity of light being received from. Uh, so basically, luminosity will change if it is going inside or outside or something like that. So the next slide. Yeah. So what are the major driving mechanisms? What are the mechanisms which drive this oscillation? So these are there are many more mechanisms, but these are the major mechanisms that we observe in stars. So the first one is Kappa mechanism. So this Kappa, must have seen this in the stellar structure equation, the initial slide. This Kappa basically stands for opacity. Sorry for my bad handwriting here. Yep. So this mainly stands for opacity, and you can see this in the first equations. This one, this. So this basically works in the energy transport equation. Okay, so let me erase this. Yeah. So what happens is that when consider like when due to this contraction or something, when the star shrinks, we have seen from the virial equation that or consider the energy conservation equation, whatever. When the star shrinks, the energy of compression, basically when the star shrinks, the some amount of energy has to go somewhere. So energy the energy which is you like when the star is compressed, this energy goes into increasing the temperature of a layer, and this can increase the temperature of a layer called as ionization zone. And there basically the degree of ionization can increase. Like consider helium or hydrogen shells. Those can heat up, and there can be like hydrogen can convert to hydrogen 1, helium can go to helium 1 2. So basically they can collect that heat when the star shrinks, and due to this the opacity increases, the gas heats up, and then this light the radiation which came and heat up that gas can go can now go out go out of the star. So this will again the loss of heat energy will uh, again cause expansion and oh wait yeah, so this will cause wait, the heat gets large. So basically the opacity increases, so it will collect more amount of heat. During expansion, the opacity decreases when it collects heat, and then when the opacity decreases, it will lose more amount of heat, and the heat is lost. So and the another mechanism is epsilon mechanism, which is basically caused due to perturbation from the energy flux, which is from the thermonuclear reactions occurring inside the star. So basically, consider a large amount of thermonuclear energy coming out of the star. This can also cause these perturbations and can cause the star to oscillate. Yeah, and another thing is stochastic processes, which is basically which are caused due to turbulence or any non-linear dynamic stuff happening inside the star. We don't know exactly how, we cannot exactly model this stuff properly, but yeah, this is also one of the major mechanism which results in this uh, different oscillation modes. Yeah, moving on to the next slide. Yeah, so we'll again first discuss the what kind of oscillations we see uh, whenever we talk about waves or something. So in this, you can see that whenever we consider a wave of mode 1, you can see that there are two nodes. If you neglect these outer nodes, you can consider one node. There in the second standing wave, we can consider one node and stuff like that. So basically, when you have oscillations inside a closed surface like this, you can consider these to be bounded within two walls like this. So this can be considered oscillations on a what do you say, on a string. So these are, so there are going to be nodes at the outer surface, and you can find, and for higher oscillations you can find nodes in between. Nodes are basically the points which do not move. So yeah, these are the standing wave oscillations that we see in uh, kind of 1D oscillations. Yeah, so moving on to the next slide. So we, similarly to how we see oscillations in 1D, there are now we can also consider oscillations in 3D. So I guess you must have seen in your your waves and oscillation course, or even in your, what do you say, uh, your quantum mechanics, basic quantum mechanics, you consider all those NLM coordinates. So basically, how do we get those NLM quantum numbers or whatever? So these are basically.
By the way, there are first years over here, so yeah, like
Yeah, yeah.
there are
So
first
I'm
years
not.
over here, so like
So I'm not going
12th
in
in the
deep
12th
into
also they
this.
would have seen a bit.
Yeah, so basically, even yeah, there are first years, I agree. uh, so basically, you already know that since like last, like how I talked in this part, there are going to be some kind of nodes in 1D oscillations. So similarly, you can expect that there can be nodes again in 3D shape. So I'm not going into the details of mathematics anyways. So you can consider that in 1D, 1D there was just, they were constrained into these two. In 2D, you can consider a basically a plane which can oscillate up above or down. So there can be different types of nodes. Like this is a 2D surface, and then in 3D you can consider this way. So basically, you need three coordinates here, n, l, and m. Here I have not considered n coordinate. So basically, you need three coordinates again, and this is similar to what we do in quantum numbers exactly. So you don't have to worry much about those right now. So basically, we need three coordinates to discuss about the oscillations that are happening inside the star. You can consider those as this n is related to the radial nodes, which you have again seen in your, like in, you have seen your 1s structure, and you can see the 2s, which is basically like this. So there is a node in between. So that's what your n means. And these l and m again are define your oscillations, in what way they are moving. I'm not going into the detail of this, so don't worry much about this. Okay. Yeah. So moving on. Yeah. What do we get from these modes? So what do we exactly get from these modes? So if you measure these oscillations, you will basically first you will get different intensities of all these frequencies of light that you will observe. You can plot a graph of it, and then this is basically a Fourier transform of that thing. You don't have to worry about Fourier transform. It basically changes your intense what do you say, your powers. You can basically get a frequency distribution of all the power distribution of all the frequencies. That's what you get from the, after analyzing your data. Don't worry much about the Fourier transform or anything. So basically, you can get a power spectrum where you can measure this power against these frequencies, all these frequencies that you can get from these modes. So yeah, basically this is the kind of data that you will usually observe from stars. This is taken from this is the data taken from sun, and I don't remember this. I guess it was Birmingham Solar, some oscillation network. Yeah, so this is the data taken from that. Yeah, so I'll move on to the next slide. Yeah, so I can discuss on this as well. Yeah, so basically in these, what you see that these are the oscillations, the waves that you can expect to see. Like what are the modes from this? So you can see that there are these standing waves around the surface of the star. This is all inside the star, and this can go have different frequencies which can help you probe deep inside the star. Like you can I think you can understand that you have seen that how the speed of sound varies differently with uh, what do you say, the density the density, temperature, and everything. Density, temperature, pressure. So the speed of sound can vary over here, and you can basically probe and use those variations to calculate like what could be the interior of the star. Okay, so yeah, we'll go to the next slide. Yeah, again, we are not going mainly to the mathematics of how we arrived at these equations. So what do we? So what I actually wanted to talk about, like what do we get from these modes exactly? Like how do we make use of them? So if you study more about this astroseismology, I can recommend you books if you want to read. So basically in astroseismology, you will get these power spectrum in this previous slide like this, and you can find out these differences. There are these certain differences which give you information about the interiors of star. So you can see these differences called delta mu 1 and delta mu naught, and this is a small delta. So what do these represent? So you can basically get these large these are called the large separations, and these small ones are called the small separations. So these are basically connected by these. You can know about the n and l from your theoretical calculations, like what number of modes you are expected to observe, and this is the correction factor epsilon here. Yeah, so basically you can find you can match the frequencies using this formula. Then how do we exactly use this formula? So from this, if you can calculate this delta, you can get these delta mu values. And since we have what do you say, we have observed like we have too many observations about our own sun. So basically we have all these values from different observations, like these r naught and m naught. We can get those values from different analytic methods. So we can basically use these separations. This dot basically means related to sun. Wait, let me get this. Yeah, so this is related to sun. This means that these quantities are related to sun. I have written there, where R sun and M sun is the solar radius and solar mass respectively. So basically, you can calculate, you can find out the. Oh wait, there's a knock at my door. I'll pause it for. Sorry for this. Yeah, sorry for the pause. I'll start again.
Okay, like Anand, I was thinking like, can we get some like 2-3 questions, like whether they are
Yeah,
like
sure.
just to see, yeah, like till now how much ever we so yeah,
Yeah,
any
I'll
quick
present
questions,
the
anyone?
slides. I can go through the slides if you want me to repeat any part.
Okay, if not, we can continue maybe.
You can write your questions in the chat box if you want. I can see
Yeah.
them later or right now.
Yeah.
Yeah. So if you don't have any doubts, I can resume. Wait, let me present it
Yeah, we can
again.
continue.
Yeah, I'll present it again the presentation mode. Yep. So where were we? Yep, this slide. Yeah. So what do we get from this data? So you can basically get the mass of the. You can basically like get that these variation data from stars which are far away from, like very distant stars, and you can basically calculate their mass and radius value. Now, why is these values so important? Like you cannot. Uh, like you may ask that we can already measure the mass of different stars. But actually, when we need to measure the mass of different stars, it's actually a very tedious process. You can like get only up to a good amount of mass estimation based on your like HR diagrams or something, and then which has basically lots of errors because you cannot get a precise measurement, and then you can get information about this mass from if that star belongs to a stellar cluster, or if they belong to what is it, binary stars. Then you can use Kepler's third law to get the mass. You know that Kepler's third law, that what was it, T cube related to mass square, or maybe vice versa, I don't remember. So basically you can use when two binary stars are rotating around each other, then you can measure the time period and you can get the mass. So these things can be used, but again these are not up to like quite certain accuracies, and again these are limited to stars which are formed inside binary star system, or multiple star system. So for the case of single star system, this astroseismology really helps in finding the parameters which we otherwise could not get a quite good estimate of. Yeah, so these are basically the two formulas which you can get from these what do you say, this uh, frequency separation. We will not go deep into the mathematics, but if you want, you can go through the derivations. Derivations. I'll I'll let you know of the book if you want. So, I'll go to the next slide. Yeah. So again, what do we get from all these measurements? So again, with this can help you get better measurements of masses and radii of different stars. So again, this same part. And again, when now you can find now you can basically find uh, probe deep inside the stars. We can basically use these frequency separations. Like here we only use frequency separations, but if you analyze all these frequencies, uh, from this you can basically get information about all like you can get information of the interiors of star at all the points. You can basically get the radius. You can basically get the what do you say, the mass distribution at a specific radius, temperature distribution, density distribution. You can also get the chemical composition of the star, and again your physical parameters, like the energy transport mechanism, like whether there will be convection there or radiation there. You can get all this information from this, and then you can use again this stellar structure equation to test your model. Yeah. So this can help us test existing theories and models, and this can also at the same time help us build better theories to predict stellar structure and evolution. So basically, you can, since we don't have any control of, like we cannot build our own star and vary the parameters and check like how your theories are working. You cannot build a star at your even a lab, and you can go on changing the parameters like temperature, densities, and stuff that can help you test your theories. So what do we have is like there we have like whole lot of stars in the universe. So what we can do is just measure those stars and test our theories. That's the only thing we have. We cannot go look when we cannot look at it at different times or something. So what we can do is look at a specific star and check if our theories are working or not. Yep. So we can do, yeah, again, similarly, like here we are doing spectral analysis of these stars. So similarly, like how we use, uh, basically, so we use spectral analysis to find exoplanets. So how does this help here? So basically, if you have astroseismic theory, uh, you know like what kind of, if you know what kind of star you have, what are the parameters. If you now know that what kind of frequencies there will be, you can find peaks. Like you can see that you can see a peak around at something like 3300 microhertz. So you can use these frequencies to filter out the noise when you are looking for exoplanets. So basically, you find an exoplanet when you can do the spectral analysis when a star is going, when a planet is going around the star. So you can expect some intensity to go down. So when the planet is transiting in front of the star, you can basically expect a intensity dip, and then there can be background noise of all these components which you can like these frequencies. Like you can also see all these things. You may not know that these frequencies, this distribution is the dipping of the intensity or something is caused by the stellar pulsation, whether it is going in and out or whether it is happening because of the star planet going in front of the star. So this can help you filter out the noise, and you can get a better determination whether you have seen a star, and you can also at the same time get a better approximation of that planet's radius and mass, and other you can use other analytical methods to find that out. So yeah, these are the benefits that you can get from it. We will discuss more about the benefits later on. Yeah. So yeah. So what? How do we test or build our theories using these as using astroseismology? So there are majorly two methods that people use. One is called the forward method. So in the forward method, you basically you have a model ready of your own. You already have a model. You just use that model and calculate the frequencies, and then you try to match them with the observed star. That's it. If it matches with the star, you can say that your theory is working. Or if you can see that there are just slight variations in the frequency, then you can find out like what's the kind of errors you are what are the kind of errors that you are getting from your models, and you can basically fit your model, adjust the parameters a bit, and find that what was wrong with the previous model, and you can build a better model. So this is the forward method. Then there can be another method called inverse method. In this, you will basically do the reverse. You will collect a lot of information from different stars, or you can just look at a single star, find out all the frequencies. You can get all the frequency distribution like this. You can get all the frequency mu i's in terms of rho and temperature and other structural parameters, and you can just basically invert that function and find density in terms of all the frequency, similarly all the temperature and mass. You can get all the parameters using this inverse method. Then you can basically build a better you can build a theory based on your observation. Yeah. So what have we learned from helioseismology? Helios basically mean your sun. So since sun is the nearest neighbor, nearest star, we can easily observe. We have like many satellites which can get us like much resolution images, like good resolution images of all this uh, what is a spectral analysis. So we can test our astroseismology knowledge there, and again we already know lots of parameters of sun you based on from different methods. So yeah, so what kind of uh, what do you say results that we have obtained from helioseismology? Yeah. So when we use this astroseismology on our sun, uh, this helped us solve the long-standing problem of solar neutrino deficiency. Like basically, you could this stellar astroseismic observation analytic methods helped us get better results of like what was happening inside the sun, and we could get better calculation of what was the neutrino generation rate inside the sun, and we can uh, like get the amount of neutrino generated based on our particle physics knowledge and stuff, and we can estimate that whether our solar model was working right or not. So this is what we have learned from helioseismology. We could solve the problem of solar neutrino deficiency. So and we get like a uh, better accuracy of finding the solar mass, which within an error of 10 kilometers, which is like a big deal because I guess I don't remember the radius of sun, but this is like considered well far less from the radius of sun. And then again, you can use this astroseismic methods to find the base of convection zones. So convection zones are basically uh, whenever you have a star, you have one core which is producing heat. So the heat energy can be transported based on two main mechanisms. One is your radiation or convection. There could also be conduction, but since this doesn't have any solid objects or uh, like the solid basically requires the particles to be very close to each other so they can transfer heat through vibration. So in the sun, this is not an efficient way. So basically the stars, the particles can radiate. Is there a question? Oh, I cannot see the chat right now. Is there a question? I'll have to stop the presentation to see the question.
Can I ask now itself, or do I have to
Yeah,
wait
yeah.
till
Yeah,
the
yeah,
end?
you can ask.
Yeah, you can
Yeah.
ask.
Yeah, you said conduction can't be possible in stars, but since stars in the stellar interior contain gas or plasma, and they
Oh, yeah.
have a coefficient of thermal conductivity, conduction can be, which is a function of its viscosity. There can be conduction.
There can be conduction, but I'm saying that this is not the major mechanism that you observe, because heat conduction requires basically the particles moving together, transfer out their kinetic energy to each other. So you can basically, due to these high temperatures inside the stars, you can basically accept these atoms, small atoms, to emit out radiation in the form of photons. So your photons can travel much faster to the outside. So these are majorly the, like, the major mechanism that star uses to transfer your heat. Of course there will be conduction somewhere, but these are so negligible that we don't consider it. And again, the your conduction may not be much directional here, because it is spherically symmetric system.
Okay.
Okay. Yeah, so basically, yeah, whenever you have a star core radiating out heat, so there can be zones like, when this can could be a radiation zone. This can, your radiation and convection zone basically can depend on the mass of stars. Like if your star is very massive, the cores can be convective instead of the core being radiative, and there can be convective just as small envelopes. It depends on what stage of evolution is it, or and we have also discussed this in the initial lecture. Let me go back to it. Yeah, so in stellar structure, you have seen that these are the mechanism for energy transport. One is radiation and convection. So you can see that whenever there is a larger temperature gradient, convection will be dominant. That's because, like, we have, convection. Convection is basically there's a large temperature gradient that the heat energy will flow up in a circular form. So that can be that can be a major mechanism in some, when the heat gradient is too large. So yeah, so in our sun, basically we have a big radiation zone inside. Then we have a outer convection zone, and we can estimate this convection zone based on this astroseismology. That's basically because there is radiation here. The so the mechanism of those modes that you have seen, that frequencies, can be different here and it can be different outside. So you can find a big discrepancy in the observation. So this can lead you to conclude that there is a sudden change between these layers. So then you can get these parallel values that uh, your convection zone lies at this 0.713 uh, solar radius. Yeah. So moving on to the next slide. Yeah. So what are the benefits that we can get from this astroseismic technology, astroseismology? So you can get, again, I'm not going to why these can get you better results or more accurate. Even I don't know properly, like how, uh, what do you say, like how efficient these are. But so yeah, basically you can get accurate determination of mass up to 10% of error, and radius to 5% error, and age of 5% error from main sequence stars and red giant stars. And again, these helps us to better understand the trends in stellar population. So like in our like basic astronomy, like how, like previously we used to estimate the mass, content, and the metallicity. Like metallicity basically means the content of other elements instead of hydrogen and helium inside the star. uh, and all this age of the star based on the stellar population. Like we can have a large amount of stars producing in a small region, and then we can consider that all those stars were basically born in around the same age. Then we can study those stellar populations and get an idea of like what could be the evolution what could be the evolution timeline for those stars. So instead of going to the stellar population, huge discussing about the huge clusters, we can basically go to single star and measure all their parameters independent of all the cluster. So you can get a better understanding of all the stars. Yeah, so what's this point? Better understanding of the effect of mass and age on stellar processes. So yeah, you can basically go measure all these parameters of different stars which are at their different evolutionary stage, and you can get models of all these stars. Like you can get models of stars in the main sequence, stars in the red giant phase, your neutron stars, or even white dwarfs or stuff like that. Yeah, and what you can also get from this, you can also get different determination of rotation rates of stars, like how these stars are rotating. We have not discussed that in detail here, but basically you can expect, like if the star is rotating, uh, I consider this. So consider a star is rotating, so it can have different speeds of rotation at their equator and even inside the star. So this differential rotation can cause turbulence and other such effects. Like these are the main effects which are main cause, uh, main things responsible for your difference in magnetic field, solar storms, weathers, and stuff like that. So basically, the ionized material can move at different speed, which can cause all those magnetic flux difference and stuff like that. So yeah, these differential rotation can again affect your modes that you can observe, and again this can result into degeneracy of all those modes, and you can get splittings of these modes. I don't know if you know this, even in your uh, quantum atomic picture, uh, you can see all those, your what your n is equal to 1 energy correspond to, and your n is equal to 2. So basically, you know that there is one s and p orbitals also here. So these also get separated because of this degeneracy. Like if you lift up the degeneracy in energy, then you can get these two as splittings. Similarly in stars, you can also expect, due to this differential rotation, there can be different energies in different points. There can be like the difference in your normal modes at some point of the star, and at different point of star. So you can expect these, and you can those again you can use your analytical methods to expect like what kind of, like how much separation you can observe, and what kind of separation corresponds to how much speed, like how fast is it rotating. So you can get the differential rotation inside the stars. You can also get how the angular momentum is being transported inside the star, how is it exactly revolving, what kind of turbulence you can expect, and stuff like that. And you can use astroseismology again, like we discussed, to get the location of convection zones, and you can also get the location of ionization zones. Ionization zones are basically where your hydrogen and again your elements are basically getting ionized there. So you can expect like these regions to be changing rapidly, like the few elements could be there which are unionized and few could be ionized. This can give you different what is spectral lines. You can basically find these locations, and these sudden changes in your frequencies, these are called as your acoustic glitches. So basically whenever there is a sudden change in, like this is consider this as a different zone. So whenever if your wave is going from this region, your whenever your speed is decreasing by a large amount, you can expect the direction or everything, the properties of the wave to be changing. So this sudden change we call as glitches, and since these are sound waves, or like these are basically sound waves, as this the surface of the star is moving up and down, so we call them as acoustic glitches. So yeah, then again we can use this astroseismic waves to determine evolutionary phase of red giants, because we can find evolution of stars based on their course exactly. Like in for red giant stars, you can expect that the core of the star to be fully exhausted of hydrogen. Then you can expect the helium to start burning in the core, and you basically have this uh, a small shell outside it, which is hydrogen, again the hydrogen which is not burnt yet. So those are the hydrogen shell burning. So since these regions change drastically in between, you can expect again these kind of glitches, and you can again get to know like what kind of what evolutionary stage the star is in. For highly evolution, for star which has oxygen burning or some higher elements burning, you can basically expect more amount of shells. And then again, with the more amount of shells, you can expect more amount of these glitches or changes in your frequency observation, and you can basically model them and get to know what is the age of that star. And you can get, again, you can probe inside the star, you can get all the parameters inside the star, and you can model them. Okay, so these were the benefits. Yeah, so now we are moving on to the conclusion, like what we can expect from seismology in the future, and like how it has helped us. So yeah, stellar oscillations are basically powerful tools probes into the interior of stars. So again, we can probe inside the stars with the help of seismology. So we do not need to send any satellite deep inside the stars to measure its parameters. We can basically measure it from outside, just having the same spectral analysis which we are using for different from different telescopes. So we can use the existing telescopes to get the data. So we don't need to make any like other equipment to get data just for astroseismology. So yeah, research in astroseismology is theoretically sound and observationally viable. So basically, you can directly build up theories, and you can test your theories based on the existing data. We have lots of astronomical data available. It is even available to general public, so anyone can build their own theoretical models and test whether their theories are right or wrong. They can even publish it. So yeah. Then there are present and future space missions which have opened up new window to like there are new missions coming up which can again help to explore uh, deep regions of uh, deep regions of the space, and you can find more distant stars. You can get more data points, and you can again, if the more amount of data points, the more you can test your theories, and again you can build a better model. So yeah, next few years we will see a big boost in stellar seismic data, which will hopefully solve many outstanding questions in stellar physics. So yeah, these are the current missions that we have. So you can see that these are the same missions that which people use for planetary transits. So basically, your planetary transit like this Kepler and this tests were made to what do you say? They were made to like find out exoplanets. So again, these instruments are measuring the same spectral analysis that we need for astroseismic data. So you don't need any different telescopes to just find out your seismological data to get to do your astroseismic analysis. You People have been using Kepler and test their theories already. So these were the missions that were working till now. You can even get public data from these, and these are the upcoming missions which are specifically designed for this. You can see that this is planetary transit and oscillation of stars. So this will be planned to be launched in 2026. So again, with this new telescopes coming up and newer and higher resolution data coming up with less and less error bars, we can expect to get even the astroseismic theories to get better, and also also the stellar models to be built better based on this, and we can hopefully understand our uh, universe much better based on the stars, because we all know that everything came from this, like, not everything, but basically stars basically gave rise to us. It gave rise to planets. And again, if you know about how a star like what are the parameters of a star, you can also expect like how what could be like how you can also expect like uh, you can also understand planetary formation based on different stars, like what could be the what is it, weather or climate or whatever around that star, and expect how the planets to be. We can also guess what do you say, if those planets are like can inhabit life or stuff like that. Again, this is a very like interesting field, astroseismology, with based on observations, and you can get very interesting results out of it. and this is a like a very hot topic in stellar astrophysics. Yep. So thanks for attending this session. If you have any doubts, you can ask. Yeah, sure. I can sell you the book, which is like highly comprehensive. You can get anything. The book is publicly available online. I will just share you the link.
If there are no other questions, we can conclude the session. Anyone else have any questions?
This is the book. This is a book written by the whole like the main pioneer, the guy, the person who has been working in this field like from like when the field was originated. So, and these are basically lecture notes. If you uh, you can try reading it. If you have any problems, maybe you can ask me. Um, like you can even contact me on WhatsApp or any other social media or email.
Yep, I think we can. Anything else? Anna, do you have to mention?
Huh?
Anything else you want to mention?
I don't know if anyone has any doubt, I can like, get them clarified or any discussions if someone wants. Okay, then I guess.
Yeah, if anyone has any further doubts and stuff, like if you want to talk about this topic, as you said, you can just like email them or text them. And yeah, Anand, maybe like put your email address or something if anyone wants to.
Uh-huh. My?
Maybe like just put your email address or something
Oh,
if
okay.
anyone wants to contact you.
Yeah, anyways, if someone wants to contact from IISER network, you can always find my email on Gmail. I will anyways write it down.
Yeah, I'd just like to thank you. It was like a great session today. Good concluding session. Kind of wrapped up everything we were doing in the past two days, past two
Thank
sessions.
you.
And yeah, like you guys can look forward to more series talks of this kind. We're like planning to have a longer series talk. Yeah, which will announce in a while. And you can find the first talk of the series on YouTube. The other two will be uploaded in like a few days. So yeah, do check it out. And thank you guys for attending. Yeah, I think we'll stop now.